Thanks a lot. So is our speaker already here? Yes, I think Marwa Assili. Could you share your screen? No? Okay, great. Thank you. So, all right, thank you very much. So welcome everybody to this afternoon session. So it is my pleasure to announce Marwa Assili from the University of Tunis El Manar. And the title of the talk is, Are You Continuous by Separating Maps? Please go ahead. Sorry, I think we can't hear you. Is it only me? No.
Hello?
Yeah, now we can hear you. Great.
Okay, thank you. It's okay? Okay. Thank you, and hello everyone. So in this talk, we try to describe relatively uniformly continuous biseparating maps. One of the relevant problems in operator theory is to describe separating maps. This problem can be treated on a different, I don't know if it's okay or no. So.
Yes, it's good.
Yes. Can I complete? I don't know.
Sorry?
It's okay?
Yeah, so fine, we can. So just go ahead. Is everything okay?
Yes.
Yeah.
Okay. One of the relevant problems in operator theory is to describe separating maps. This problem can be treated on a different manner depending on domains and codomains on which maps act. Perhaps the most important theorem to Arendt, who proved in 1983 that an order-bounded separating linear map between two algebras of scalar-valued continuous functions in a compact topological space is automatically a multiple of a positive algebra homomorphism, that is a weighted algebra homomorphism. Using various types of domains, many mathematicians have worked on generalizing the Arendt theorem in several ways. So in 2000, Henriksen and Smythe gave an algebraic version of Arendt's theorem. Later in 2003, Boulabiar, Busquets, and Henriksen proved a Riese-space version of Arendt's theorem for order-bounded separating linear maps between two unital F-algebras. So our work is based on the work of Boulabiar, Busquets, and Henriksen. The order-bounded condition will be removed and substituted by a continuous condition. So we prove that every relatively uniformly continuous linear biseparating map between two phi algebras is a weighted isomorphism. Moreover, if there exists omega, a positive element omega in E such that T omega is invertible in F plus, then T is positive. And we finish it by a Banach-Stone type theorem for biseparating maps. So I need first to start with some definitions, which will be used throughout this talk. Let's recall that there is space E, which is also an associative algebra, such that the product of two positive elements is also positive, is called the lattice ordered algebra, or briefly an algebra. The lattice ordered algebra is said to be an F algebra whenever the following condition is true. By an almost F algebra, we mean an L algebra in which F and G equals 0 implies Fg equals 0. Let E be the space. We say that a sequence Xn in E converges relatively uniformly to X in E if there exists a positive element E, U, such that the following condition satisfies. We denote this by Xn converge to X RU. We say that a sequence Xn is a relatively uniformly Cauchy sequence if there exists a positive element such that the following is true. An Archimedean Riese space is said to be relatively uniformly complete if any relatively uniformly Cauchy sequence is relatively uniformly convergent in E. An operator T between two Riese spaces is said to be positive if Tx belongs to F plus for all positive element X in E. An operator T is said to be order bounded if T maps order bounded subsets of E into order bounded subsets of F. T is said to be disjoint preserving if modulus Tx and modulus Ty equal 0 for all xy in E such that modulus X and modulus Y equal 0 in E. Let's recall the definition of relatively uniformly continuous. So, a linear map T between two Riese spaces E and F is said to be relatively uniformly continuous if Xn converges to 0 relatively uniformly, implies then Txn converges to 0 relatively uniformly. Note that every order bounded operator is relatively uniformly continuous. We say that the linear map T from E into F is separating if Fg equals 0 in E, implies that Tftg equals 0 in F. Note that on algebras of real or complex valued continuous functions, the concept of linear disjoint preserving map coincides with the concept of linear separating map. So, by Erickson and Johnson, an Archimedean F algebra with identity element is said to be P algebras. Now we are able to announce our result. So let's start with the following lemma. Let E, F be two Archimedean Riese spaces with F relatively uniformly complete. Then every relatively uniformly continuous disjoint preserving linear map from E into F has a unique disjoint preserving linear extension from ERU into F. So according to this lemma, we have the following proposition. So let E and F be two Archimedean Riese spaces and T from E into F be a relatively uniformly continuous disjoint preserving linear map, then T is order bounded. So according to the previous result, we know that T has unique disjoints preserving linear extension from ERU into FRU if we want. So, and by known result by Abramovich and Kitov, who said that an order relatively uniformly continuous disjoint preserving linear map from ERU into FRU is order bounded, and therefore T from E into F is order bounded. Now we consider E an almost F algebra, F semi-prime F algebra, then every relatively uniformly continuous separating linear map from E into F is order bounded disjoints preserving linear map. So according to this result, we note that all results that have been made for order bounded disjoints preserving linear map remain available for relatively uniformly continuous separating linear maps from almost F algebras into semi-prime F algebras. As an application, we have the following. Let E and F be two phi algebras, that is Archimedean F algebras with identity element, and T from E into F relatively uniformly continuous linear biseparating map. Biseparating that's mean separating, bijective, and its inverse is also separating. Then T is weighted isomorphism. That is, there exists an isomorphism C from E into F, lattice isomorphisms and algebra isomorphisms, and an invertible element W in F, such that TA equal WCA for all A in E. So here, by Boulabiar, Henriksen, and Bisques, every order bounded disjoints preserving every order bounded disjoints preserving map between two phi algebras is weighted isomorphism. And since every relatively uniformly continuous linear biseparating map is order bounded disjoints preserving map, so we have our result. Note that the previous result is also true for complex case. The next result, we need the following lemma. So let E and F be two phi algebras and T from E into F be a relatively uniformly continuous separating linear map. If E is the unit of E, then we have the following equality: TFTG equals TE TFG for all FG in E. So let EF be two phi algebras, T from E into F be a relatively uniformly continuous separating linear map. If there exists gamma in E plus such that T gamma is invertible in F plus, then we have T is positive. As an application, we have the following two results. First, let EF be two phi algebras with identity elements E1 and E2. T from E into F be a relatively uniformly continuous biseparating linear map such that TE1 equals T2, then T is positive. Also, we consider X and Y two topological spaces and T from CX into CY biseparating linear map such that T1 is invertible in V plus, then T is order bounded. So before to give the Banach-Stone theorem, we need to recall the definition of with real compactification. So let's start with these definitions. Resolved space X is said to be completely regular if for each X in X and for each closed subset F of X, such that X does not belong to F, there is a continuous functions such that Fx equal 1 and Fy equal 0 for all Y in F. And the topological space X is said to be real compact if X is homeomorphic to a closed subset of the Cartesian product of R. So let's recall that every completely regular space X have a unique real compact space denoted by nu X having these two properties. X is dense in Ux and Cx is algebraically isomorphic to C nu X. This space nu X is called the National real compactification of X. So the function h from X into Y is said to be homeomorphism if H is bijective and both H and its inverse are continuous. If such a function exists, then X and Y are homeomorph. So let Xg be a metric space, E be in X such that the distance of E into B is positive, then we have the following result. Also, let Xd be a complete metric space and X belongs to the real compactification of X, then X belongs to X if and only if X has a countable neighborhood based in Ux, the real compactification of X. So now we finish it by the Banach-Stone type theorem. Consider X and Y two completely metric spaces. Then we have the following. Say X is isomorphic to Cy as unital vector lattices if and only if X and Y are homeomorphic. Moreover, every unital biseparating map T from Cx into Cy is of the form Tf equal f from H, where H from Y into X is an homeomorphism. There are some references, and thank you so much for your attention.
So thank you very much for your interesting talk.
You're welcome.
Does anybody have questions, please?
Yes. Yes. Yes.
Please, yes. No. Any questions?
I have a question.
Yes, sure.
Can you go to the slide where you define linear separating maps?
Okay. Yes.
Yes. Here, so E and F are two V spaces. And how is the product defined? You say the product is 0 in E, then the product of TF and TG is 0 in F. How is the product defined?
The problem is?
I just want to know how the product of F and G are defined in general Rie spaces.
So I think E and F should be Rees algebras here, right?
Then it would be fine.
Yes, in fact, in semi-prime F algebra, having that F and G are orthogonal or the product is null.
Can you repeat? Excuse me.
So here, I think that she wants to say that F and G are orthogonal, so are TF and TG.
Yeah.
Wouldn't that be then disjointness preserving?
Yes, it's the same thing, but in lattice algebra, they
same.
said separating or biseparating when they are bijective, but disjoint preserving or
Are
disjoint
the
preserving.
same.
Okay.
Okay.
Also, I have a question. When we define the area continuity, we use sequences. Is there a difference between defining area continuity with sequence or with nets?
There is.
Is there some difference if we define area continuity or area convergence with nets and not with sequences?
I don't know. I don't try to.
Because when we define order convergence, we define it with sequences, with the nets, and not with the sequences. And are you sure that we define also the area continuity with sequences?
I don't know. I don't understand what you.
When we define the order convergence, we use nets. And order continuity for operators, we use also nets. For area,
Yes.
here you use for the area
continuity. I use sequences. Nets.
But you write everywhere that they are sequences.
But it's not available for nets.
Okay, thank you.
I would suspect, but I'm not quite sure, that the definitions are equivalent for sequences and nets, because somehow, if you go down to a principal ideal with the gauge norm, then somehow norm convergence in this principal ideal. For norm convergence, net convergence is the same as sequence. So net continuity is the same as sequential continuity. But maybe one has to be careful whether one can choose the same regulator or something like that, if one goes from nets to sequences.
No, there is two, because Zanen, I think that Zanen uses also sequences, but we have a lot of problems with the closure. The closure with the sequences are not closed, are not area closed. So there are a lot of problems with them. So that's why I asked if you really use nets or sequences.
I guess so. Admittedly, I'm not quite sure, yes. So maybe let's keep this as an interesting question, whether RU continuity is the same for sequences as for nets. Thanks for the question. Further comments or questions? Okay. So, well, then let us thank the speaker once again.